In this chapter, chapter 8, you'll study the dynamics of circular motion. So this concerns things like an object that's moving in a circle, and it has an angular velocity. Basically, the angular velocity is a measure of through what angle it rotates through in a given amount of time. So this equation tells you the angular velocity. Of course, this is analogous to this equation for linear velocity, for translational motion. The connection between linear and angular quantities is given by this formula. And this comes from the fact that an angle in radians is just defined as the ratio of the arc length. That means this distance, so as an object moves from here to here, it's that distance divided by the radius of circular motion. If an object is moving faster and faster, then it has angular acceleration, and angular acceleration is measured by the rate of change of angular velocity, analogous to linear acceleration, which is the rate of change of linear velocity. Objects executing circular motion also have a resistance to being rotated, and that's called their moment of inertia, given by this equation. For a bunch of point masses, the moment of inertia is just the sum of all the masses times the distance they are from the axis of rotation squared. This is analogous to mass in translational motion, which is the resistance to being accelerated. Also, an object moving has kinetic energy, given by this equation. An object rotating has rotational kinetic energy, given by this equation. It also has angular momentum, which is analogous to linear momentum. And of course, the thing that causes rotation is a torque. Torque is the product of force times moment arm. And the sum of the torques cause angular acceleration, analogous to the sum of forces causing linear acceleration. As an object moves from here to here, if we look at an object along this line, it has linear velocity and it also has angular velocity. The connection between the two is given by this formula here. So its linear velocity depends on how far away it is from the center of rotation. So let's apply some of those formulas. First of all, how do you find the center of mass of a bunch of point particles? Or the center of gravity. So the equation for the center of gravity is given over here. So basically what this means, this is a one-dimensional problem, so we're only going to be concerned with this part. That the center of mass of this system is just the sum of all the masses times their positions divided by the sum of all the masses. So in this case, this will be the 5 kilogram mass on the left multiplied by its position plus the 3 kilogram mass multiplied by its position on that line plus the 4 kilogram mass multiplied by its position divided by the sum of all the masses. That's a 5 plus 3 plus 4 kilograms. And if you do the math here, the position comes out to be at -1. In other words, this point here, right here, will in fact be center of mass of this system. An example of a calculation to calculate the moment of inertia. What resistance, for example, does this system have to being rotated about this axis, the y-axis right here, the green line arrow? When you calculate the moment of inertia, you have to specify what the axis is that you're rotating about. So for example, if I move this line over here, the moment of inertia of this system is now different. When I move it here, the moment of inertia of this system is still different. So let's start off with this problem. What's the moment of inertia about that axis? So here's the equation. See if you can stop the tape and see if you can find the moment of inertia. So using this formula, we find out that the moment of inertia is going to be the first mass, which is 5 kilograms, times its distance from the axis of rotation squared, plus the second mass times its distance from the axis of rotation squared. And since it's right at the point, it basically turns out to be the contribution for the 3 kilogram mass turns out to be 0, plus the 4 kilogram mass times its distance from the axis of rotation squared. And if you do all this out, you will find out that it's 96 kilogram meters squared. You can also find the center of mass for a two-mass system like the Earth and the Moon. So, for example, this is the Earth on the left and the Moon is on the right. The distance between the Earth and the Moon, center to center, is 60 Earth radii. And it turns out that the Earth is 80 times more massive than the Moon. So where along this line would the center of mass be? So in order to answer that, we're going to use the formula to calculate the first formula here. There's two masses only. So the first mass is the Earth. The mass of the Earth is 80 m, and its position is 0. We're going to measure the center of mass away from the center of the Earth. How far away is it from the center of the Earth? So it's going to be somewhere along this line over here. Plus the second mass, which is the Moon, whose mass is m. If the mass of the Moon is m, then the Earth is 80 m, because it's 80 times more massive than the Moon. And of course, its position is 60 Earth radii. And you have to divide this by the total mass of the Earth and the Moon, which is 81 m. So if you do the calculation, this is 0, the first term is 0, so we have 60 mr divided by 81 m, and this turns out to be 0.74 r. So basically that means that the center of mass of the system is inside the Earth, right around here. Since this is r here, this is a bit less than r. And that would be the right answer. And usually you can see in this little simulation where the center of mass of a two-mass planetary system is. And if you make one of the masses bigger, then the center of mass gets closer to that bigger one. So right now, if B is quite a bit bigger than A, the center of mass is right outside of B. And it could also be actually inside of B. This is more or less the way it is with the Earth-Moon system. So what causes rotation? For example, you want to open the door. What do you have to do? Well, you have to apply a force, but there's more than that to it. You have to apply a force at a particular place. So applying a force here is different than applying it here, in terms of how easy it is to open the door. So the thing that causes rotation is a torque. The torque is a product of the lever arm times the force. The lever arm being the perpendicular distance from the line of action of the force. That's this line right here. The distance, perpendicular distance from that line to the center of rotation. This is that distance right here. Actually, it's D. This is the perpendicular distance from that line to the axis of rotation. That's the lever arm. So if I apply the torque, for example, if in the middle, somewhere or even closer, then that lever arm is a small number, like in this particular case. So I apply a force of 300 newtons, and I apply it here half a meter away. The torque I'm applying is 150 newton meters. If I apply it at 2 meters away from the axis, from the hinge, then I have a torque that's twice as big. So the torque is the tendency of an object to, the tendency of a force to rotate an object about some axis. And this is very important, about some axis. So how do you find the torque exerted by a force if you have if the force is at an angle? Well, there's a couple of ways to look at it. This 300 Newton force can be resolved into components that we have on the bottom here. 300 newtons this way is actually a pull this way and a pull that way. The pull up is 300 sine of 60, which is 260, and the pull to the right is 150. That is a 300 cosine of 60, which is 150 newtons. So basically, we just replace these two forces, but this force here, 150 Newton force, exerts no torque because it has no moment arm. It goes right through the axis of rotation, so therefore has no moment arm. And the other force, 260 Newton force, does have a moment arm, and therefore it exerts a torque. And that torque is just equal to 150 times 2, which is 300 Newton meters. So let's take a look at this problem where we have two forces acting on an object. We have a force of 300 newtons pushing up, and we have a force of 300 newtons at an angle of 30 degrees. And the question is, the 300 Newton force here is at 1 meter, 0.8 meters, I'm sorry, 0.8 meters, and the 300 Newton force on the end here is at 1 meter away. So each force exerts torque. So the torque due to the first force, that one here, is just force times moment arm. (240 Newton meters). The torque due to the second force, let's call it T2, is going to be, well, we have to find the two components of this force. So the one that we're looking for that exerts the torque is going to be the Y component. So it's going to be 300 sine of 30, and the distance, the moment arm, is 1 meter. And so this comes out to be 150 Newton meters. Now, any torque causing these two torques cause the door to rotate in opposite directions. The first force will tend to have the door rotate this way. The second force on the right here will tend to have the door rotate that way. So they have opposite signs. They work against each other. Normally, counterclockwise, we call positive. So this will be a positive torque, and this will be a negative torque. So the sum of those two torques is just, this is a negative number, keep in mind, 140 minus 150, which is 90 Newton meters. Now, if the door has a moment of inertia of 180 kilogram meters squared, what would be its angular acceleration? Similar to linear acceleration, where acceleration is force divided by mass, in rotational motion, angular acceleration equals the net torque divided by moment of inertia. This is sum of force divided by mass. The net torque we already found is 90 Newton meters. The moment of inertia here is 180 kilogram meters squared. So the angular acceleration is 0.5 radians per second squared. So this is another example that shows you how to find the torque. This is a fan. So when the fan blows, there's a force due to air friction this way. But if you turn the fan sideways, facing the inside, the table does not rotate because there's essentially no torque in this case over here. The table is rotating about this point, and the force goes right through that point. And in this case, the force has two components, and only one of those components exerts any angular acceleration. The other thing about rotational motion is rotational inertia. How hard is it to rotate something? And basically this depends on how far apart the masses are, the masses that make up the thing you're trying to rotate, from the axis of rotation. So say you want to rotate these weights here. These masses are pretty close, and it's pretty easy to rotate opposed to this mass. This is much harder to rotate. Same thing here. This has a higher moment of inertia or rotational inertia than this because the masses are closer together. We can calculate the rotational inertia of a system of masses by using the formula for rotational inertia, which is that I is equal to the sum of all the masses times the distance that they are from the axis of rotation squared. So here we have this mass is R, this mass is R, this mass is 1/2 R, and this mass is 1/2 R also. So the rotational inertia of this system is, well, we have M, each of these masses is M. They just are different positions. So M times R squared plus the other M on the other side times R squared. All right, so these are the two M's we just did. Plus, now these M's here, these are going to be M times 1/2 R squared, plus again, the other one is also 1/2 M times 1/2 R squared. And if you add all these up, you will see that they come out to be 0.25 kilogram meter squared. So coming back, let's keep this in mind that the moment of inertia of this system is 0.25. 0.25. So let's go back to the next problem. If I equals 0.25 kilogram meter squared, and if I apply these two forces, each of these forces exerts a torque, what will be the angular acceleration? So again, from alpha equals net torque times I, that's the angular acceleration. Now what's the net torque? I, we know, is that number over here. Or what's the net torque? These two forces exerts torque. So the net torque is equal to the first force, which is 10 newtons, acting at a distance of R. The other force is 10 newtons, but acting at a distance of 1/2 R. And also it's in the opposite direction. So one of these torques is negative, and basically this is, we're going to choose counterclockwise negative, so this one is negative. It's minus 10. So this equals minus 10R plus 5R, which equals minus 5R. So putting those back into this equation here, that's the torque. This is the moment of inertia. If we do that, we get Let me erase some of this so you can see it better here. Let's take a look at this particular problem. Now this uses the fact that something is rolling, it has rotational kinetic energy. And we can write that down as kinetic energy rotational as 1/2 I omega squared. Something is moving, just plain old flying along, it has translational kinetic energy equal to 1/2 mv squared. Now in this case, this ball is rotating, it's rolling, and it's moving down the plane, so it had both of these energies. So the total energy at the top, and it's over here, equals the total energy at the bottom. At the bottom, it has both energies. At the top, it only has mgh, and at the bottom has both. Now, for a wheel's moment of inertia is 2.5 mr squared. That's I. Down an inclined plane of height h without slipping. What is the velocity of the sphere at the bottom? So we want to solve this equation here for v. Given the fact that I here is 2/5 mr squared. Now, it would appear that there's two unknowns here, but these two are connected to one another by the equation that connects linear and translational motion is that v is equal to r omega. So we're going to substitute for omega here v over r. So here it is. This is omega. It used to be omega, and this is I. 1/2 I omega squared. And just solve this equation, all the masses cancel off and all of these. Solve this equation for v, and you get that v is equal to 4/7 gh. We will now look at the conservation of angular momentum. Just like linear momentum, there are no external forces acting on a system. Linear momentum is conserved. So in the case of angular momentum, if there are no external torques, then angular momentum is conserved. Angular momentum being the product of the moment of inertia times the angular velocity. This is angular momentum. This is similar to regular momentum, which is mv. So what this means is that if somebody is on a rotating platform that's rotating, he has angular momentum equal to I times omega. If he brings the weights in, his moment of inertia gets less because the masses are closer to the axis of rotation. But there's no external torque, so in order for this product to stay constant, if I gets less, omega must get bigger. So as an example, supposing your physics professor is standing on a rotating platform with a lovely girl on each arm. The platform is rotating at an angular speed of 4 radians per second, and the moment of inertia of the system is 200 kilogram-meters squared. If he now proceeds to pull the girls closer to him, reducing his moment of inertia to 100 kilogram-meters per squared, what is the new angular velocity of the system? So, I times omega initial is equal to I times omega final. Initially, the platform is rotating at 4 radians per second, and the moment of inertia is 200. So this is the initial angular momentum. If he pulls the girls in, I drops to 100. So what is omega final? So that 200 times 4 equals 100 times omega final. Well, omega final must be double, so it is 8 radians per second. And you get that by dividing both sides by 100. Let's look at a few equilibrium problems. An equilibrium problem is a problem where a system is just standing there. It's not moving, it's not rotating, it's just standing there, and usually try to find some unknown force. If it's completely equilibrium, that means all the forces in both directions must add up to zero. That's the first condition of equilibrium. The second condition of equilibrium is all the torques about any axis you want also have to add up to zero. You choose which torque you want, or what do you want to take torques about. So let's look at this sample problem. A 60 kilogram man stands on a platform, a 2-meter platform held by 2 strings. The uniform platform weighs 200 newtons. What is the tension in the strings? So the first thing to do is draw all the forces acting on the system being the plank. So the first thing is that there's a force here because the guy's standing here. And 60 kilograms, this is 60 times G. Let's use 10 for G, so it'll be 600 newtons. There's also a force here right in the center. And that's equal to the weight of the platform, which they tell you is 200 newtons. So given this, what are the readings of T1 and T2? So let's use the first condition of the equilibrium. All the forces have to add up to zero. And there's only forces in the y direction, so they have to add up to zero. So that means that T1 plus T2 have to equal all the forces down, which is 200 plus 600, which is 800 newtons. So we know that T1 plus T2 add up to 800, but we don't know what T1 and T2 is. We can surmise that because the man is standing closer to the T2, that T2 will in fact be bigger than T1. But let's see if that's true. To find this out, we need to take torques about some point. We can choose any point we want, but let's choose this point right here to take torques about. So the sum of the torques around that point have to add up to zero. Now we have two forces that cause counterclockwise torques. That's the 600 meter and the 200 meter. So let's look at the 600 Newton, 600 Newton force. The torque exerted on that will be minus 600 times 0.5. The torque exerted by the 200 Newton force will be minus 200 times 1. Now it's 1 because it's right in the middle over here, and the total plank is 2 meters. Plus, this T1 exerts a torque in the opposite direction. Actually, this should be opposite sign, so these are clockwise, so this will be positive, positive. And the next one will be negative. (200 times 1), and T1 times 2. So this will enable you to find T1. 0.5 times 600 is 300, plus 200 equals to 2T1. So T1 is going to equal to 500 divided by 2, which is 250 newtons. And now we know over here, we go back here, calculate what T2 is. T1 plus T2 is 800, so 500 plus T2, which is what we're looking for, equals 800. And we can see that T2 is going to equal to 300 newtons. So as we surmised before, T2 is bigger than T1 because the guy is slower. T1 is 250, T2 is 210. As a final example, you can look at this problem, very similar, where the man is standing here, so there's a force down here, there's a force in the middle, and there's two tensions up. This force is 500 newtons. The distance here, the total distance across from here to here, is 10 meters. The plank itself weighs 100 newtons. And the question is, what is T1 and T2 in this case? So stop the tape and try to work this out. So this is the solution. T2, check your calculations, is equal to 300. T1 plus T2 add up to 600. So T1 also is equal to 600. Is also equal to 300 newtons.